Beth.
And I'm Beth.
Welcome to Physics with Beth and Beth. Hello and welcome to Physics with Beth and Beth. I'm Beth. We are on our very last video in Newton's Laws. We're heading to Unit 3 in our next videos. We're still working on the center mass. We just posted a video about center mass for a rod, and then a rod of uniform density, and then a rod with non-uniform density, using these integrals. Because remember, in this AP Physics C or Engineering Physics, we're taking it up a notch from AP Physics 1 and adding that calc piece. All right, so we're going to do a triangle. This is going to be center of mass for rigid shapes. All right, and I'm actually going to do the triangle. I know it's really one of the most common out there that we do the center of mass on, in my opinion, anyway. So we're going to do the triangle. All right, so I've got this triangle drawn. This is the y-axis, this is the x-axis, so that we can kind of get some perspective here. Again, terrible at art. I say this on almost every video. My colleague Beth, amazing artistic ability. So this is pretty terrible triangle here, but the big triangle, that's in the black marker here, it has a height of h, it has a length of L, it has a mass of M, and it has a width or a thickness of T. We're going to call that T for thickness. All right, so that's it. Now, we know when we're using integrals, we're adding up, we're dividing this triangle into an infinite number of infinitesimally small rectangles. All right, and those rectangles are going to have a mass of dm, just like when we were doing the rod. They're going to have a length here of dx, again, just like the rod video we did. But now they're going to have a height. We're going to call this height y. And that y is going to be changing, because if it's here, it's a smaller y than it is in that rectangle, right? And then it's going to be getting even longer, the y value. So it's changing. We always got to think about what is changing when we're doing these integrals. All right, dx is not changing. dx is still the same for both. So they have a mass dm. They have a length of dx, and they have a height of y, and they also have the same width. The width of the triangle is the same, or the thickness of t. So those are the same, that width or thickness in both the rectangles and the triangles. Okay, in the rod we did linear mass density. For this rigid shape, we're going to be using volumetric mass density. Volumetric mass density. Okay, we still have the same formula. We still have the same problem that you can't take the integral of x in terms of mass. You can only take the integral of x in terms of dx. So we need an expression here for dm that's in terms of dx. So we're going to start here, and just like we did with the rod, we're going to say, hey, that little rectangle has a dm is its mass, and its volume we're going to call now dv. And I should have said that. The volume here for the triangle is v, and the volume for the little rectangle is dv. All right, so that means if we do just like we did with the rod, I'm going to kind of ignore this in the middle, that my density, if I multiply dv over, dv equals dm. Okay, so I now have an expression for dm. It's still not in terms of x though, so we're going to have to deal with that in just a minute. In fact, let's just go ahead and deal with it now. I've got a volume of a triangle. Okay, well, the volume of a triangle is 1/2 base times height times width, right? So 1/2 of the base is L, height is H, and the width we're calling T for thickness. So it's 1/2 LHT. That's for our triangle, the whole volume of our triangle. But now, if you want the volume of our little piece here, dm, that's a rectangle. So it's not 1/2 base times height times width anymore. That's the volume of a rectangle. So our dv is not going to be 1/2 LHT. It's going to be the height times base times the width. The height of those little rectangles are y. The length of them is dx, and the width of them is the thickness t. So that's what our volume for little dv is. Okay, so I'm going to plug that in for this dV. My volume of my rectangle, again, height times base times the thickness for a rectangle. All right, so I'm going to sub that in right here. So now I have center of mass equals 1 over the total mass of the triangle, x, and for, I'm going to need that expression for dm, but let me not skip this. I'm going to go rho, and for dv, I'm going to plug in y times my thickness times my dx equals dm. Again, where did I get this? That is the volume of that rectangle. Base times height times thickness width. So base times height times the width, the thickness. All right, so now I have a whole expression. Now I have this whole expression for dm that I'm going to put in right here for dm. It's rho y thickness dx. Okay, now I'm getting somewhere. I have x in terms of x. This is good. By the way, that's thickness. That's the t for the width. All right, perfect. All right, now, first thing we do in an integral, we gotta take the stuff out that's constant. We gotta get this out. All right, for the whole triangle, my rho is constant. It's mass over volume. So I have 1 over m. I have x. My rho here, my volumetric mass density of the triangle is constant. It's mass of the triangle over the volume of the triangle. I still have y, and I have the thickness, which stays constant. It doesn't matter if it's the little piece or of the rectangle or if it's the whole triangle. The thickness just stays the same at thickness, and we have dx. All right, now I'm going to pull out everything that's constant. All right, first of all, I already have 1 over mass here. My mass of my triangle and my volume of my triangle stays exactly the same. My thickness stays the same. But look at my y. We said my y is changing. As x changes, my y changes. Okay, this is new for us. We've got 2 things that are changing, and so we can't pull that out. So that's x, y, dx. And what are my limits? It's going from L to 0. All right, so it's going to be from L to 0. And you're like, oh, can I take y in terms of x? No, you cannot. You can take x in terms of x, but you can't take the integral of y in terms of x. So we're going to have to deal with that in just a minute. Let's deal with one thing at a time. I'm going to cancel out my masses. All right, so I have x, my center mass equals 1. Oh, equals, that's just 1. So, and I've got my thickness over volume, times that integral from L to 0 of x, y, dx. But I know that I have an expression. This is volume of the triangle. We said that, hey, I put in the volumetric mass density of the triangle. The mass of the triangle, the volume of the triangle. That's the volume of the triangle. And that T is just the thickness of it. So I came up with an expression for my volume. I'm going to put that in here. So I have my center of mass equals that thickness. The volume of the triangle was 1/2 the length times the height times the thickness. All right, and that's going to be from L to 0 of x and times y dx. All right, well, my thicknesses go. That's good. That's 1/2 in the denominator, so that flips. So I'm going to go all the way up here, and my center mass is equal to 2 over length times height of that triangle. And then I'm at L to 0 of that x, y, dx. Okay, so again, the 1/2 just flipped, so we have 2. The thickness is canceled, and we have over L times height, and these are of the triangle. All right, we got to figure out how to get y in terms of x now, because I can't take y, the integral of y in terms of x. So I'm going to draw out this triangle and try to blow it up so you can see this. We're going to use similar triangles here. This is theta. This is going to be one of my little rectangles. All right, we know it has a height y, and we know it has a base of x, right? Because x is that distance on the x-axis. So, and if the triangle were over here, it has a longer x, right? All right, now let's look at the triangle itself. The triangle itself is L and height is H. Okay, makes sense? All right, so now we're gonna go, hey, that's opposite over adjacent. So I'm gonna go tangent theta, and I'm gonna deal with the triangle first. Is H over L. Opposite over adjacent. All right, well, now I'm gonna go to the little rectangle. The little rectangle is still tangent theta for that little guy. All right, or I should not say rectangle, I'm sorry, I'm saying rectangle. The little triangle this makes, because now this is a triangle, right? I have my rectangle at the end, and I have the distance from the x-axis. So now I have, let me draw that out, and I've been saying rectangle, but I meant the little rectangle here is the end of it. So this is a little triangle. So we can compare the little triangle to the big triangle, right? Similar. So so we're gonna call this big triangle, and we're gonna call this little triangle. Okay, so my little triangle has opposite as y, and the adjacent side is x. Okay, look at this. If tangent theta is equal to h over L, and tangent theta, and it's the same angle, these are similar triangles, equals y over x. Can't we set these two things together? We can. All right, so h over L equals y over x. Now remember, I'm looking for an expression to put in here for y in terms of x. And I just found it if I multiply x to both sides. So I have the height of that big triangle times x over the length of that big triangle equals y. I now can plug that in here. So that's the extra step when you're dealing with this rigid shapes. First of all, in this case, we're using volumetric mass density. And on top of that, you've got the volume piece. You now have to figure out the volume of the triangle, and it's different than the volume of the rectangle because the volume of a triangle is not the same as volume of the rectangle in formulas. All right, you're still putting in, we've got this rho dv equals the dm, but we've got to figure out that expression for dv. So the volume of the rectangle times your volumetric mass density equals dm. We subbed that whole thing in. So now we have in terms of dx, but we've got this y issue when we get down here. So we're going to use these similar triangles and figure out a relationship for y, or an expression for y in terms of x. Sometimes you just have to stop and go, oh my word, what in the world did we just do, right? You kind of get lost in the weeds of the problem, I like to say. So now I'm back at this center mass equals 2 over LH. The integral from L to 0, it's where we're evaluating this integral. I still have x, but now I have this expression for y that I'm going to put in here. H x over L. Okay? And that times dx. Okay, now I'm going to pull out things, because now look, I have only x's in terms of x. I'm like getting there. We're almost there. I'm going to pull out things that are constant. Okay, first of all, h is constant, so I'm pulling it out, and L is constant, and I'm left with from L to 0 of x squared, because I still have two x's, x squared dx. All right, now I'm going to, let's see if I can draw here. Oopsies. Go here, give myself some more room. All right, now my h's cancel, and I have x center mass equals 2 over L squared. All right, I now can evaluate this integral. It's just x cubed over 3 from L to 0. So my center mass, 2 L squared. That's L cubed over 3 when I put L in, and then 0 cubed over 3 is just 0. Again, I have my 2 L's on the bottom, 1 L on top. My 2 lengths cancel with 2 lengths in the numerator, leaving me with 1 length. And I have that my center of mass is 2/3 L, which makes sense that if this is halfway, that you have more mass on this side, it's got to be towards the end. And that is how you do that. So several more steps. Remember, you got to figure out your volume of your triangle or whatever your rigid shape is, and then you have the volume of the rectangle. These are 2 different volume equations because you have 2 different shapes here. All right, then once you plugged in and you found what dV was, you could plug that in. Then we have to go, oh my rectangle, my little rectangles are changing their Y value as well as their X value. So I had to go over to my geometry and figure out the relationship between this little triangle and the big triangle. And you're like, you said it was a rectangle. Yes, this part was a rectangle. True story. But we're looking at that rectangle. If we put that rectangle there, it makes a little triangle, so we can compare. The tangent theta is h over L, and then tangent theta is that y over x, opposite over adjacent. And we end up with an expression for y in terms of x to plug in for our y in our integral, and then we just solve, and you get 2/3 over L. So that is about as hard as it gets, these rigid shapes in center of mass. So if you can follow your rigid shapes using the integral for center of mass, you are golden, because this is about as hard as it gets for center of mass with rigid shapes. All right, thank you for watching. If you haven't subscribed, we would love that, or share with your peers if they need help. And thank you for watching, and happy physicsing.